Session 22, and we are very glad to introduce Professor Juyong Zhang from USTC of China and Shunsuke Saito from Meta. So the first talk is from Professor Juyong Zhang. Let me first introduce Professor Zhang. Professor Zhang is a professor in the School of Mathematical Science at the University of Science and Technology of China. He received his BS degree from the University of Science and Technology of China in 2006 and the PhD from Nanyang Technology University at Singapore. His research interests include computer graphics, 3D computer vision, and the numerical optimization. He serves as the associate editors for IEEE Transactions on Multimedia and IEEE Computer Graphics and Applications. So today, the talk from Professor Zhang is monocular camera-based high-fidelity digital human modeling and animation. So let's welcome Professor Zhang.
Okay, thank you. Can you hear me?
Yes.
Okay. Okay. First, thanks for the kind introduction. Hello, everyone. I'm Juyong Zhang from USTC, and I'm honored to be invited to give this talk about monocular camera-based digital human modeling and animation. Okay. So recently, VR, AR, and the metaverse attract a lot of attentions from industry, academic. And for example, some bigger companies like Microsoft and Meta, they invested a lot of manpower and resources to do build their system, like Microsoft's Fusion 4D and Meta's Horizon Workroom system. So what these systems need to effectively and efficiently digitalize the real physical world, including the environment, the object, and especially the human, including the shape and motions. So currently, digital human has been already successfully applied to movies like the left one, the Anita But Engine, and the right one, the Ready Player One. And another application example is Google's Starline, which is Google's next generation 3D video chat booth. So you slide into a booth, and your image is supposed to be projected to another booth in real time, as if they are actually sitting with somebody else across a table. So in this system, they first reconstruct the digital human and transfer the reconstructed model to another side. Currently, the most popular approach is based on camera array. For example, as shown in this slide, one of the most famous example is Jason Huang's digital human. Its digital human has been used for the presentation of 2020 the GTC conference. To digitalize Jason Huang, they utilize our camera array, including around maybe around 100 cameras to capture multi-view images, and based this based on this well-constrained lighting and camera setup, it can recover high quality geometry shape, appearance, and lighting, and it can suppose further editing. But however, it still has some limitations, like require constrained capture environment and needs a complex modeling process, and the cost of this hardware and the modeling process is quite expensive. So therefore, it can only be used for top companies and research labs. So recently, some research effort is divided to this sparse camera-based digital human modeling. For example, based on this 3 to 5 cameras, they can recover high-quality geometry shapes and motions, and synthesize lower view and lower motions. We can see that the cost and the capture convenience has been greatly improved compared with the camera-only solution. However, this kind of capture hardware is still out of reach for the general public. So this is because it is almost impossible to do camera synchronization and calibration for ordinary users. So our target is to do this digital human modeling based on just one single camera. The reason is that we will have like this smartphone, and we can use our smartphone to easily capture a short video. So as shown in this example, we can use this smartphone capture a very short video, like maybe 20 seconds, and we design several algorithms to reconstruct its corresponding geometry shape and motions for the face, for the head, and the body. So based on this reconstruction result, we can use that for the many upstream applications. So our group has conducted some research effort toward this target. Maybe around 4 years ago, we adopted this parametric 3D face shape face models like a 3D morphable model and face warehouse to do this 3D face reconstruction and tracking from just one single view image. As shown in this demo, based on this input one single view image, we can recover its corresponding smooth surface shape, and the rendered result is also quite okay for the face part. But we can see that based on this parametric model, which only contain around 100 parameters, so the strength part is that it has a fast computation speed, and meanwhile, due to its low dimension representation formulation, it has limited representation ability. For example, it can only recover the face part without the hair and the teeth part. So therefore, it is more suited for the tracking task rather than the high-fidelity reconstruction task. For the human body, we also conducted some research work about this closed body modeling from a single input image. We also achieved this target based on this constructed parametric model. So this paper is published in 2020 ECCV. As shown in this example, so this is the input image, and we can do body and clothes reconstruction simultaneously. Similarly, it has limited representation and generalization ability due to the constructed low dimension parametric model. For example, as shown in this 3 examples, the clothes has been separated as 2 parts, but the input image they just has one skirt because but it failed to recover this skirt because the parametric model doesn't have this type of clothes. Okay, this is what we did in this based on this parametric model for the head, for the face, and the human body. So our first work in this direction is this prior guided multi-view head reconstruction. So the input is with some sparse view image. What we wanted to do is to design our algorithm to reconstruct the whole head model with hairs. So actually, this is a very first work toward this. Not only the face part, but what the whole head, including the hair. So this paper is published in Transaction Multimedia, but actually this work has been finished around 2019. Okay. So the main idea of this work is include 2 parts. different from existing mesh-based representation, like a 3D morph model or face warehouse. We didn't utilize the mesh representation. We adopted this linear implicit function-based SDF, like it means that side distance function to represent the reconstructed head model. We also to guide the reconstruction process, we adopted the differentiable rendering to do this kind of self-supervised reconstruction process. So actually in 2019, so the LORF is not published. So we at that time we use this based on this IDR. It's actually based on this differentiable surface rendering, not volumetric rendering. So okay. Meanwhile, we also utilize some priors like this landmark and face passing and this 2D direction of the hair part. So we use this kind of prior information to guide the reconstruction process. And the surface is represented by this kind of linear implicit function based on SDF. And we guide this reconstruction process based on this differentiable rendering pipeline. Okay, with this kind of a lower design, we can recover high-fidelity reconstruction result. Okay, let me give some details. Okay, so first, because for this kind of nonlinear optimization, we need to give a good initial solution. So we utilize this parametric model. So we utilize this 3D morph model recover from this multi-view image. We do this kind of inverse rendering and recover the identity and the expression coefficient to recover its corresponding initial surface shape. And based on this kind of loss, it's like a photometric loss and landmark and this regularization. And we also we get this semantic labels such as shown in this here. It's like the loss and the face and here. It's like this to do this face passing. Meanwhile, we also recover the hair. So we to do this two-dimension direction detection for the hair part, and from this 2D we recover its corresponding 3D direction, and we utilize this the above mentioned three kind of priors to guide the reconstruction process. Okay, let me show one example. As shown in this example, the user can directly use this smartphone to do self-capture or ask his friend to help capture the video. During the capture process, the user keep as rigid as possible based on this captured multi-view image. So as shown in this slide, from this short video, maybe just like 10 seconds, we can reconstruct a high-fidelity geometry shape and corresponding textures. Okay, we show more result. We can see that with only a short video, we can recover high-quality surface shape of the head part, including the tooth and the eyes, and different from parametric models like 3D morph model or flame, which can only recover the face part. Our method can recover the whole head model, and the reconstruction accuracy is much better compared with this this kind of parametric models. So the first work is only for this static head part, but it's only recover this static and cannot be animated, which limit its applications. So Meanwhile, it requires that the user keep as rigid as possible during capture, so which is not convenient for some users. So therefore, we extend this the last work from static to dynamic, and it has two benefits. First, it frees the user to arbitrary expressions and motions, and thus can be easily captured. Second, the captured video contains the user's personalized expression information, and thus the recovered head model can be used for animation and retargeting. This is a pipeline. Actually, the pipeline is quite similar with the last work. So the input is a monocular video with arbitrary pose and expression and motion, and output is an animatable high-fidelity head model. As a different frame has different expressions and poses, so we first to utilize this parametric model to initialize the deformation between different frames. So because the different frame has different expression code, and then adopt this deformation field to further refine the non-rigid deformation. Similarly, we also adopt the facial prior, including this semantic segmentation, landmark, and parametric model to do this initialization and constrain the reconstruction result. And so the main difference from this pipeline and with the last pipeline is that because this is a dynamic video, so different frame has different surface shape. So we adopt this like a dynamic deformation field to model the non-rigid deformation. Okay, so this shows some result. So the input is okay. Let me play again. So this is the input single video. We show that we have the whole algorithm contains several component, and like this with only deformation, without segmentation, without this kind of 3D morphable or frame. We combine this together. We can say that the final result is much better for just one component. Okay.
Excuse me, Juyong. Actually, I cannot see the video very smooth.
Okay, maybe we just continue.
Yes, sorry for the delay. Yeah.
Okay. I'm sorry. So so here we show some result. Okay. So we can see that the input is just a single video with different poses and expressions. So the second column shows the rounded result, which quite close to the input, and the final column is shows the reconstructed surface. We can see that we can recover the whole head the whole head part, including the hair, for each frame. And based on this reconstruction result, we can use another input video to do this retargeting for this kind of reconstructed result. Okay, so we just introduced two works for this head reconstruction for static and dynamic. So we also extend this kind of method for closed human body reconstruction. So we also just based one single video. Okay, so before design the algorithm, we need to first know what are expectation to human body reconstruction. So the first is that the capture hardware should be one single camera, such as a smartphone. In this way, every people can use his smartphone to do this capture. And the second that is the capture process should be easy. As shown in this example, the people just rotate before the smartphone, so the capture process is quite easy. And the final requirement is that the reconstruction result should be high fidelity. So this just show one example. This is a algorithm pipeline. The key idea is that we adopt this explicit and implicit geometry representation. So the reason why we utilize this both representation is that the mesh-based representation is very suitable for this kind of forward deformation. So as shown in here, so we do this kind of long-rigid deformation for this mesh representation, and non-rigid deformation plus this scaling-based deformation. So we formulated the whole non-rigid deformation. And but as we know that the mesh representation is has some limitations, like this kind of fixed topology, and it is not differentiable. So based on this reason, we also adopt this implicit representation. And based on this implicit representation, we can utilize this inverse rendering. So currently there are a lot of work. So for example, this news or IDR, something kind of this method. We can use this photometric loss to back propagate this kind of information to update this SDF-based surface representation. So in this part, because this the capture process is dynamic, so we have this, we design this differentiable non-rigid recasting in this paper. So based on this kind of, we put all this together. We design this whole pipeline, and so we show some result. And okay, so the left shows the input single view video, and the right is show the corresponding surface reconstructed surface shape for each frame. We can see that we can recover the whole closed body, and especially for some challenge cases like this this hair and this skirt, and we can see that we can reconstruct the result is quite good. And based on this, we this kind of designed algorithm, we develop an application in App Store. It called linear scan, and you can download and try it. So it is this application is designed for this human body reconstruction. We also try this kind of designed algorithms for some challenge cases. For example, we can say that okay, let me play the video. We can say that it's some good result can be obtained for this challenge case, because we can say that the people is just walk around and sit on the chair, and yeah, definitely it has some not good result for some part, but we can further improve the result, and we believe that it can be get better for these challenge cases. Okay. After we introduce this kind of surface reconstruction for the head and the body, we also consider also consider that if the final result is just for rendering, do we really need this surface mesh representation? So based on this consideration, we we develop our algorithm called this kind of nerve blind shape for head part for head reconstruction. So we know that this mesh blind shape is is quite popular for this face animation. For example, as shown in this video, so this is the input video. This is a recovered corresponding expressions, and its expression can be represented by this linear compilation of the predefined linear base blind shape. So we just for each frame we can just recover its corresponding coefficient. So okay, so if we just recover this this video, do we really need this mesh representation? Therefore, we develop our algorithm called this nerve blind shape. So the this is traditional mesh blind shape formatted in this way. For arbitrary expressions, it can be represented by a linear compilation of this kind of blind shape. So instead of combining bases in mesh representation, we generalize this concept of blind shape from mesh to linear radiance field. So we adopt a multi-level voxel field as blind shape basis, so which enables strong representation ability on the aspect of rendering and fast training. So this is the main idea. So in the left is a traditional mesh blind shape, and this part is the nerve-based blind shape, and we update or optimize the corresponding nerve-based blind shape based on this rounding loss to back propagate to get this corresponding nerve-based basis. Okay, so this is a input. It's also just a single view video. Okay, so this is a capture process. And this is a whole algorithm pipeline. So we first do this kind of face tracking. We get the corresponding coefficient, and we fix this coefficient. And the coefficient is not optimized in the optimization process. So this is what we need to optimize this H1 to HK. This is it represents its corresponding nerve-based basis. We utilize this multi-instant NGP, means multi-resolution hash encoding to represent this nerve, and we use this kind of rendering loss to refine or update or optimize this corresponding basis. Okay, so this is a optimization process. So the input, this is the input video. This is the intermediate result of the optimization process. We can say that it takes around 20 minutes. We can recover all the corresponding nerve-based bases, and the final rounding result is quite close to the left one. Yeah, I also know that it also have some artifact. It's kind of like say, okay, here the tooth part is missing, but this year has a lot of following work to can get a much better result. Okay, so actually we also apply this kind of based on this idea, we apply this idea to some product. So the left is the input video, driving video, and the right one is the already recovered, offline recovered head model. So we can use this nerve blind shape using this drive video to do expression retargeting for the reconstructed nerve-based head model. We can say that though the input is just a single view video, and it is real time, and we can say that some macro expressions is also quite good. Okay, let's get faster. We also extend this head nerve-based head dynamic head reconstruction for this dynamic human body reconstruction. So this is our recent paper published in TVCG. We call it intrinsic NGP. So we utilize this intrinsic coordinate for this hash encoding for human nerve. So the input is also a single video. It takes around 20 minutes. And then recover its corresponding closed human, and based on this recounted human recounted result, we can do this lower value synthesis and shape editing. So the first is that so it is based on this instant NGP. As we know, maybe last year, instant NG get attract a lot of attention from computer graphics and 3D vision because it's very fast for nerve training. It like takes 5 seconds for some for some scenes like this one. However, it is originally designed for static object or scenes. In their multi-resolution hash encoding, the input is absolute Aladdin coordinate. It's like here. So it is designed for static scenes. So we wanted to extend this this instant NGP from static to dynamic human body. What we think about is that although the human body is dynamic, but actually the coordinate is we can reformulate the coordinate from the absolute coordinate to relative coordinate. So what we did is utilize this simple model. So we recover simple model for each frame, and we do this 2D polymerization. So we get this UV coordinate for each surface because they will share the same message topology, and so they share the same UV coordinate. And for each 3D dimension coordinate in the whole 3D space, we can compute its newest point on the sample model. For example, for this X, we can get its corresponding point P here, and P has this UV coordinate. So this is the UV coordinate for the X, and this distance we call it D. So we convert this the original 3-dimension space to this UVD space, and we use this UVD coordinate for this hash encoding. In this way, although the human body has different poses, so the relative coordinate is keep as original as possible. Meanwhile, we know that this maybe this projection is not accurate enough, so we also further optimize this offset field. Is optimize this UV coordinate for each 3D coordinate for each 3D points here. So we have this offset field to further improve the corresponding UVD coordinate. Okay, let me show some example. We compare our method with this animatable nerve and human nerve. I guess so. This is yeah. This is the human nerve is should be from Washington University, and this is from Zhejiang University, and we can say that based on this, based on our design, our method can converge very fast. it takes around maybe 10 minutes, can get a quite a good result. Okay. So because we based on this sample model, so we can do some shape editing. We can just change the corresponding coefficient for the sample-based representation. Okay, we can make the neck stronger, or the body shorter or fat. Yeah, something like this. Okay, so after we do a lot of this kind of surface reconstruction, nerve-based reconstruction, so it's just for reconstruction. And for the real application, we need to do this kind of expression transfer or post-transfer or retargeting. And another popular application is this like kind of, we just input some text or voice. We wanted to drive the reconstructed digital human. So this just show one example.
大家好，我是央视新闻 AI 手语主播。从北京冬奥会开始，我将全年无为听障用户提供服务。手语主播，冬奥会开始。
So okay, from this example, we can say that so we can know that this digital human is not real, right? So it's so it's not real enough. Based on this, we have one work about AD-LERF. So AD-LERF is published in ICCV 2021. So the basic idea is very simple. So we just know the mapping from the voice to the talking head based on this LERF representation. Because actually we do this kind of audio-based talking head maybe 2 or 3 years ago. It's so the first work we try to use this mesh-based representation like a 3D morphable or frame, and we just use this voice to drive the mesh and then render the result. But we find that the result is not very good. After NERF is published, we think that it's a good chance to can get a better result based on this NERF representation. So the basic idea is very simple. This is NERF, and we just add this kind of feature of this voice. We call it A, and the corresponding human pose, the head pose, this rotation and translation. And we do this, we learn this mapping from this this feature to the feather, color, and density. Okay, so let's show some result. So this is a digital human reconstructed this our LERF-based representation, and we just input some text or voice. Okay.
大家好，我是神会数字人平台生成的雪莉，很高兴认识你们。我可以做好多事情，可以唱歌。
When I was young, I'd listen
Spanish as well.
对话定在中街道。
こんにちは、私はシェリーシュです。これは私の日本語の声です。
Okay, so we can also use this method for this presentation. Okay, show in this video.
大家好，我是象眼实验室李东。首先，非常感谢大家来参加我的浙省自然科学基金委意识与重建和博士均。这个工作中用到每个体素的颜色和密度。
Okay, maybe we just need to conclude my talk. So, we can first we can reconstruct the high-fidelity digital human based on just one single video with this linear implicit representation and this inverse rendering framework. And for the future work, we can further improve the capture convenience and the computation speed and the reconstruction quality. So, for example, robustness to the illuminating the human motion and challenge expressions. And maybe currently the computation, the reconstruction speed is not very good because it also need to take maybe 20 minutes on the desktop. Maybe for the future work is how about it directly computing reconstruction on the mobile device? And yeah, actually for this single video, the most challenging part is to fuse this motions or different expressions or poses, fuse them together to recover the the motions and for the static the standard surface shape. So this is a very challenging case. So how can we combine or fuse different frames or with non-rigid deformations, non-rigid deformations together to recover this all this informations is also challenging. Okay. Yeah, thank you. That's my talk. Okay.
Okay, really appreciate Professor Juyong for the fantastic talk. Actually, I'm also doing research in the area of digital human, and I have read a lot of papers from Professor Juyong. And I have a little question. So okay. I noticed that you also made several products using based on implicit representations or nerves, and including an app on the App Store or many other production level systems. So I was wondering, so can you share a little bit about the biggest challenges for creating such a system for monocular digital human reconstruction for consumer usage?
Yeah, very good question. So actually, for this kind of product, maybe our the main product is this like kind of voice driving talking head. I think the most challenging part is that for the ordinary users, so they just use his smartphone to take a short video, and actually it's so but they don't care about the lighting condition. For example, in my current situation, the lighting is not very good, and so for the for many users, so they have very different challenging cases. So have various conditions. So we need to design our algorithm very robust to handle these challenging cases, some core cases. So this part is very challenging. So it's not. So for our research, we just maybe it works for some 10 examples. It's good enough. But for this product, you have a very challenging different conditions, and you need to handle most of these challenging cases.
Okay.
For example, for this kind of segmentation, and for relighting, and for maybe for some landmark detection. So you need to consider all of these cases.
Yeah. Actually, the whole pipeline is actually a little bit long, so any part could be erroneous. Yeah.
You mean which part is?
So any part have the opportunity to break. So you need to handle every model in the whole pipeline.
You mean which part of the whole pipeline can be handled?
I mean, for such a complex system, it contains many modules, for example, segmentation, detection,
Yes.
reconstruction, animation, etc. So every part is very we need to make sure every part is robust enough to make it very robust. Yeah.
Yes.
Yeah. Okay. So due to time limit, we don't have any other questions. So let's thank Professor Juyong again for the fantastic talk.